So the next thing I'm going to put up is a Leaving Cert question based on a question that came up in 2017, which is a Redox Titration. Now in the Leaving Cert, you are always given the relative atomic masses to use. They usually round it up. You're given Avogadro's constants and any other units or constants that you need, you're given that. Then you're given the question, which is a Redox Titration. There's going to be some other questions, and this is just the calculation part of the question. To start with, if I was answering this in the Leaving Cert, I would highlight some of the figures that were given. So we're told that there's a solution of hydrated ammonium iron sulfate as a primary standard prepared by dissolving 8.82 grams of the crystals in dilute sulfuric acid. So we know that this is related to this. So we're going to be able to work out the number of moles of this using the grams, and we're going to be told the volume, so we're going to be able to work out the concentration of that. The standard solution was titrated in 25 centimeters cube portions, and we're told that this is the volume of the potassium permanganate that was required. Now, the questions are usually scaffolded. So we're asked in the first question, find the number of moles of iron 2 plus ion in a 25 centimeter cube portion of the standard solution. Okay, if we're working out the number of moles of iron 2 plus, well, before I can work out the number of moles of iron 2 plus, I'm going to work out the number of moles of the compound in total. So we're going to work out the number of moles of NH4,2SO4.FeSO4.6H2O. Don't worry about those dots there. Here we've just got a water crystallization. We're not going to worry about it. All we're going to do is, whenever you're working out the number of moles of a substance, just like I said in the previous reactions, use the figures you're given and use your equations. Mole equals mass over mR equals 8.82 over mR. Now, I need to work out the mR. The mR equals all of these things added up. Okay, so it's going to be 14 plus 4 by 2 plus 32 plus 16 by 4 for the 4 oxygens plus iron, which in the question they've given me as 56 plus 32 for sulfur plus 16 by 4, which is 4 oxygens, plus 6 by 18, because there's 6 water molecules. That gives me a figure of 392. So our moles of that substance there, the ammonium iron sulfate, 8.82 divided by 392, which is equal to 0.0225 mole. So what we've worked out there is that there are 0.0225 moles of the compound in 250 centimeters cubed. That is, there are 0.0225 moles of this compound present in 250 centimeters cubed. But we know that in every one of these I've got one Fe2 plus. So what we worked out, as I said, is there are 0.0225 moles of this compound in solution. Well, for every one of these, there is one of these, so therefore there is 0.0225 moles of iron 2 plus ions in the 250 ml solution. Well, if there's that many moles of iron in 250 centimeters cubed, but we're asked how much moles of iron were there in their 25 centimeters cubed that we took out of that, well, 25 taken out of 250 centimeters cubed is 1/10 of it, so therefore we have 1/10 of the number of moles of iron if we're taking 1/10 of the volume. So therefore, in 25 centimeters cubed, there are 0.0225 divided by 10, which equals 0.00225 mole, which equals 2.25 by 10 to the minus 3. Now let's just go back up to the question. We're asked for the number of moles of potassium permanganate required to oxidize this quantity. Now, the number of moles of potassium permanganate that reacts with Fe2+. Here's where we use our mole equation. Here's where you use our mole ratio. We know that for every 1 manganate, it reacts with 5 irons. 5 mole Fe2 plus reacts with 1 mole of MnO4 minus, which are manganate. So if 5 forms 1, then this will form 1/5. It's going to be 0.00225 divided by 5, which equals 4.5 by 10 to the minus 4, which is just 0.00045. Okay, so in solution, there are that many moles of manganate when it reacted with this many moles of iron. Remember, that's in the solution that reacted with 25 centimeters cubed of the iron. So, according to titration, that many moles of the manganate reacted with the iron. Well, if we want to work out the concentration of that, then what we need is the volume and the number of moles. So, C equals N over V, concentration equals number of moles divided by volume. Number of moles is this, and volume is just 20.45 centimeters cubed, because that's given in the question. So the concentration then, just go back to black, concentration is 0.00045 divided by 20.45 over 1,000, which is equal to 0.022 mole per dm cubed. And that's just the same as 0.022 capital M for molarity. So just to recap then, we first asked to find the number of moles of iron 2 in a proportion of our original sample, which is our standard solution. Well, we can only find the number of moles by taking the mass, dividing by the MR. We find the MR, we divide the mass by the MR, and that gives us the number of moles of our compound. We know that if they're specifically asking us for Fe2 plus, because they just want to reduce the complication of dealing with this, then for every one of these is one of these. So we know the number of moles of Fe2 plus in the original sample. We need to work out the number of moles of Fe2 plus in the 25 centimeters cubed that was taken out. We work that out. Then to work out the number of moles of manganate here, we needed to use the balanced equation, the stoichiometry of the reaction. To find out the actual number of moles of manganate, we use the actual number of moles of iron 2 plus that reacted and divided by 5, because they react in a 1 to 5 manner. So we divide by 5 and we get the number of moles of manganate. From the number of moles of manganate and the volume of manganate that reacted, we're able to work out the concentration of the original manganate solution, which is this.